Hello. Hello and good morning to Room Ravioli. Our next speaker, our first speaker of the day obviously, is going to be Král from Elasticsearch, and he's going to speak about Beyond Search.
Thank you. So, can everybody hear me? Okay, great. Great. So that part is working. So let's hope the rest goes as well. So what Elasticsearch is, it is a very what we say is very buzzword compliant thing. It has all the cool buzzwords. It's REST based, HTTP. It uses JSON to communicate. It's fully distributed. It does search. It does analytics. It does most of that in real time, or what we call near real time. It is very scalable, and it's open source and based on Apache Lucene, which is a very mature implementation of inverted index and a lot of the search-related stuff written in Java, one of the most advanced search engines out there. What Elasticsearch does is it enhances Lucene with a lot of functionality in its core, and also provides a distributed layer for your document. So I'll jump right in, since there already was an introductory talk by Dougal. So if I'm going too fast, or if I've skipped over something, just raise your hand. We'll deal with it right on the spot. Most of the talk will actually be in the form of live demo, when we'll show how you would typically use Elasticsearch, what are the possibilities, and see how we're going. So let's start with the most simplest use case. Just use Elasticsearch as you would a document data store. So you can very easily just store some documents. It's HTTP, it's REST, so you just put a document. Notice that there are two words here. The first is the name of the index, the second is the name of the type. So I'm using the index stack, which for us will mean Stack Overflow. I've actually taken some data from the publicly available data dump of Stack Overflow, and that's what we'll be using as our test data. So something real, not something contrived. So the first command is just basically asking a question. That's just some placeholder document, but it should demonstrate how it actually works. So index, type, ID. I can also get it and delete it. So far, nothing too interesting. Any database or any data store can do this. So let's move over to search. Search is where the core of Elasticsearch is, as the name would suggest. And these are two very simple ways how to do search. This first one is basically a way that we provide for convenience, so that you can try it out. When you just install Elasticsearch, which is a fancy word for saying download and run it. No need to install, no need to anything. Once you have Java, you just install Elasticsearch, you untar it, you run it, you're done. So you can do this. You can call this URL from a browser. It will actually work. What usually you'll end up using is the query DSL. So the endpoint is the same. It's _search, and we'll see more variants of that later on. And what this does is it basically takes a query in the Lucene syntax and just executes it. But there is a little problem with this. The Lucene syntax is very powerful, and you can do a lot of that. But you really don't want to be in the business of concatenating strings and passing them on to the database. We've usually all been there, and it wasn't a very nice experience. So what is instead, what we'll do is we'll use our own query DSL. So this is a pretty simple query for Elasticsearch, and we'll now go quickly through it and see the difference. So queries are composed of filters and queries. Filters, range filter right here. Filters are Boolean. A document either matches a filter or it doesn't. No other options. Filters are very fast. Filters are cached. So if you use the same filter over and over again, it will be cached. Also, the individual filters are cached. Later we'll see how we can combine queries and filters. The filters are cached at the lowest possible level. So if you have compound filter, it will just use the caches for the individual sub-filters and use them to compute it. So even when one of your filters is changing, you will still be using the cache very effectively. So that's why, rule of thumb, always use filters unless you absolutely must use a query. And the difference, query does not only tells you if your document matches, but how well does it match. It will calculate a relevance score of the given document based on a lot of factors, based on the fields that match, based on any potential boost factors that you provided with your business knowledge, based on the term frequency in that document and in the other documents across your entire data set. So this is pretty much the same in every search engine, so I'll not go into detail. We can go at the end if somebody has questions. So what does this query actually do? So it's a filtered query, so it contains a query and a filter. Filter just limits that we want everything that has been created after January 1st, 2012. And the query says that it must match Python in either title or body. This tells us that title is more important for us. We've boosted it with a factor of 10. And it must not match PHP in the title. So pretty straightforward query. And this will be our starting point for further. That'll be our starting point for further exploration. So I have a similar query here, but I'm really sorry I couldn't be showing you the data from Stack Overflow because I just don't have enough space on my hard drive. So for the actual live demo, I just took the data from DBA Stack Exchange. So instead of programming languages, we'll be talking about databases. So I've rewrote pretty much the same query using MySQL. I'm using curl commands to actually execute everything. And notice that I'm talking to an index that's called dbastackexchange.com. I'm only searching for questions. And so you can see already that the endpoint search can already be on the index level, on the type level, or on the cluster level. That means that we'll search across all the indices. I could even do something like this, which will search over multiple types. I could do the same for the index. So let's see what happens when we actually execute this. Data. Say that you believe me that these are actual questions from DBA Stack Exchange, and we can actually do something about this. So what we'll do as the first alteration to our query, the query remains the same. I've just added a line to limit the fields that we want to return. Usually there's not much use for this in your application unless you have some really large fields that you don't want to be getting back. But if you actually want to be showing it off at a conference, it's very useful when you can actually see the documents that were returned. So you can see here is the document ID, the index where it's stored, its score, so how relevant it is to our question, what type it is, it's a type of question, and the two fields that we requested, creation date and title. So far, nothing surprising. I'm going rather quickly over the examples. Feel free to raise your hand if I'm going a little bit too quickly, or if you feel that I've skipped something. If you feel like that, there's more than likely that somebody else feels like that too, so it will not be wasted time. But we've also searched over the body field, and I don't want to return it whole because that would be unreadable, especially with this font size. So what I'll do is I'll add another component to the query, and I'll ask Elasticsearch to highlight the results for me. So I'll ask to highlight the results for fields title and body. I'm just limiting the fragment size so it's not too big, so it can actually again fit on the screen. And what this actually means is pretty print again. I'm pretty printing here using just Python, but you can actually append a question mark pretty to any Elasticsearch URL, and it will do the pretty printing for you. I just wanted the actual shell files to be as simple as possible. So this is already here. We see that we have returned the body and the title with a list of matches where you can see the parts that match our query. So the parts that are MySQL are highlighted using HTML tags. Of course, we can override that and choose either different tags or a different method of highlighting entirely. So this would be very difficult to do on the client side. Not only would you need to get the entire document or entire body field and then search for the MySQL, but because the data are matched based on further criteria. For example, we'll match it even if it's in different case. We'll do stemming before we do the search. So for something like MySQL, it's not much difference. But for example, imagine that we were searching for Postgres instead. So we would be searching for Postgres, but we would naturally expect the database to find Postgres and PostgreSQL and PGSQL, because all of these are synonyms for Postgres, and we can tell Elasticsearch when we create an index for DBA that those are synonyms. So if we search for Postgres and it would find PGSQL would be highlighted, which is not trivial to do in your application. You would basically have to duplicate the entire logic that you got Elasticsearch to do for you. So just to show off a little more, a colleague of mine actually wrote a little tool just to pretty print the result of the query. So this is how it looks. Unfortunately, it doesn't really fit to the width with this font, but this is basically the document. This is how we'll be looking at it now. So we have the ID, the title, the metadata information, so score, index, type. We have the fields that we want it returned, creation date and title, and we have the highlights actually highlighted in ANSI colors. So what do we do next? Next, let's start complicating things a little bit. So far, we've only been searching for MySQL. So let's search something that has MySQL but also doesn't have NoSQL. So we are looking for questions that somebody asked, that somebody is asking about MySQL, and he is not mentioning NoSQL. So what we did is, instead of just the multi-match, we suddenly have a bool query here. And a bool query has several parts. So there's must not, and should. So must and must not are pretty obvious. The should clause would contain queries that are optional, but would contribute to the score of the document. So a document that would match not only the must clause, but also any queries from the should clauses would get higher up in the result list. So I'm pretty sure that nothing has changed. We still get all the documents that are relevant to us. We didn't see any NoSQL before, so this is basically just a step in preparation for the next one. And before we actually get there is one more theoretical thing we need to talk. So our prayers have been answered, because so far everything is working. Let's hope it will hold if we get into more interesting stuff. And this is what I wanted to talk to you. Typically, with document stores and search engines, you work with individual documents. Elasticsearch has two ways to actually introduce some actual relationships between documents. The first one is parent-child. In the data set that we have, we'll be using it to represent the relationship between a question and an answer. So we are saying that an answer is a child of the question. And what this enables us to do is we can search over the answers but return the questions. So we can filter the questions based on their answers, and vice versa. So how it's actually set up, when you define the mapping, which is the sort of schema for the type. So here we are defining the type for answer. We'll just say that the parent is of a type question. And then when we are indexing one answer, we'll just notify Elasticsearch what the parent is. This is very important because this enables Elasticsearch to store the parent and the child in the same shard, on the same machine in the cluster, so that this join is actually possible, because otherwise it would be a very, very expensive operation. So once we are using the parent-child relationship, we need to make sure that we always specify the parent when we are dealing with the child, because that determines where the child is stored. And this, of course, allows us to do the has-parent and has-child queries. So this is an example of the has-parent query. So we are querying answers, and we are looking for parents, so for questions that mention Python in their body. So this will return us all the questions to the answers that mention Python. How is that useful? Let's see what we can do with this. So we ended up with in the last step of the demo, we ended up searching for questions that contain MySQL and not NoSQL. So what we'll add is we'll actually add a has-child query. So we'll look for questions that mention MySQL, don't mention NoSQL, but one of their responses do mention NoSQL. So we are basically looking for questions that have been trolled. Somebody's looking for a problem with MySQL, and somebody's offering a solution with NoSQL. Not very helpful, but we've all done it. So unfortunately, if we actually run it, there's not much difference, because we are still only returning the questions. So we have no idea who the troll is, what's going on there. We have just limited the question. So if we actually wanted to print this out to the user in a web interface, that would be useful. For us, we'll just rewrite the query to work the other way around. So we'll just do. Right now we are searching for answers. So I turned the query around. I'm searching for answers whose parent mentions MySQL and not NoSQL, and the answer mentions NoSQL. This is just to show how composable and flexible the DSL is. You can take the core queries, so the match, the multi-match, and other, and compose them using the compose queries, bool, has-parent, and everything. Yes? I'll repeat the question.
Take off the boost thing on the titles, because you have the...
So yeah, I did take off the boost.
I'll just repeat it. When you switch this around, did you deliberately take off the boost on the title? Is that a limitation, or is that just like a typo?
It was something in between a typo and a deliberation. I just wanted to fit on the one page, because I tested it with a slightly smaller font. But there was no reason for me to do so. The score of the parent will actually contribute to the score of the document. I can actually even control that, so I can say whether it just contributes or it doesn't, or there is actually also a has parent filter and stuff like that. Good catch, by the way. I was pretty sure nobody will notice that I'll be able to get away with it. I have to be more careful in the future. So we've done the query is not interesting. We've just turned it around. It looks very similar, but it does the exact opposite thing. So when we actually run it, finally we have something interesting. So yeah, by the way, your schema looks like something which could fit into NoSQL solution. Seriously, like somebody's asking for help with MySQL and you're just going to troll them? No. So this is just there to show that I was not lying when I was claiming that the query works in a certain way. This is exactly what it does. So back to the original query. And what we'll do now is we took the original query, which is here, the query filtered, and we wrapped it once more in a custom query, just to show you one more type of query. And what custom score query does is it will allow you to transform the relevant score of the given document. If you have some business knowledge, for example, imagine that you have a site, a QA site, where the individual users can vote how good a question or answer is. Once I learn to type, I'll show you that I can then introduce a script that will actually take that into account. So I'm taking the original score, adding 1 because it looked better in the result. You probably want to have some more complicated math formula here than what I'm doing here. And I multiply it by the rating of the document. So I take a number from the document, the popularity, and I will say that these documents are more important. So it's not the same as boosting, which was shown in the score as well, but this is just taking the raw value of the score, the flow value, and passing it through a transformation. So what this will do is, if we actually examine the results, so we start with, at the very bottom of our search result, we have something with rating 1, and we see that it has two matches, one in title, one in body. It has a score of 2.9. If we go up, we have something that has rating of 3 and only one match. So we can already see that it's actually working. It has a rating of 3, so it's potentially 3 times better than the previous document. And if we go further up, we have something that has a rating of 1, but it has a lot of hits. The relevancy was really high before we actually started transforming the score. So this just shows you that it's not the same as if we were just sorting by the rating. We are sort of taking the rating that's our own value and the relevancy score taken from Lucene, taken from Elasticsearch, and we are combining them to provide better results. Either something that's very relevant or something that's not as relevant, but it's very good. So just one query that will allow us to see some more power of Elasticsearch. So now we start with the same query, so we still have the script, we still have the fields and highlights and everything, and we add one last thing. And what we add is actually facets. So what facets are some sort of aggregation field. So right here we are asking for tags and frequency. And tags is a terms facet, and it uses the field tags. That's very fancy and very cryptic, and what it actually means is, give me all the tags that occur in this result set, in the entire result sets, not just the 10 items that I'm being returned, and just sum them up. So we'll see the distribution of tags across this result set, a tag cloud, if you will, and do a similar thing for dates. So take every month and give me how many. We are still searching for questions. So how many questions were there during that month? And this is something that runs very effectively in Elasticsearch, even on large data sets. And what it actually does is exactly as described. So we see the facets, so we see the frequency for each month, we see the number of questions. For each tag, we see the number of occurrences. So this is a very powerful thing, and we are slowly running out of time. So this is a very powerful thing for either faceted navigation. So for example, if you ever searched for a hotel or anything, on the left side you had the number of hotels that have 3 stars and 4 stars. That's where it came from. That's just a facet that will tell you how many hotels matches your search criteria that have 3 stars, that have 4 stars. When you click on it, typically in the web interface, it will just add the filter. So this is where it came from, and that's one big use case for it, the faceted navigation. The other use case for it is actually doing analytics. So this is Kibana. This is an open source plugin for Elasticsearch. It was developed to work with Logstash for analyzing logs that are stored in Elasticsearch. But I like to use it to demonstrate what facets can actually do. So I'm searching across the index. I have some hits here. I can click and see the individual fields that compose that. I have the distribution over time in here. I can just zoom in. I have the tag cloud right here. So PostgreSQL 6%, SQL Server 25%, a sad state of our database market. And we have the distribution across number of comments. So 0 to 2 is 357, 2 to 4, 4 and more comments per question. Where this is amazing is it actually enables us to combine the analytics with the full text search. This is what I was saying when I was mentioning near real time. So currently, this is just a couple hundred megabytes of data running on my machine. We have actually customers that have tens of terabytes of data in one cluster, and they're running analytics like this. And because of the distributed nature of Elasticsearch, everything works just fine. Just to finish the very quick overview of the additional features, nested is another type of relationship. We are using that for comments, which basically means take the comments and embed them into the original document. We can still search over the comments. We can even facet over them and get the data for the individual comments. So this would be a query that would search for a question or answer where there is a comment that mentions Python and is written by somebody from Italy. So a search on a nested document. And the last feature I want to mention is the Percolator. So the Percolator is reversed search. So you will index your queries, and then you will run your queries basically with the document. So you have an index queries, and you will just send in a document, and you will receive the list of the queries that actually matched, the name of the queries that matched. So right here, I'm creating a query that's called conf. I'm looking for anything that has conference in its title. It should be title. And then I'm just sending in a document which actually has a conference in the title. So the result of the second call would be, oh, the conf query matched. So this is a very efficient way, very easy way how to implement saved searches, alerts for your users. For example, if you have a job board, you can very easily let the users define their own queries using the whole power of Elasticsearch DSL, and then just alert them when there is a new ad matching their criteria. So I'm afraid we don't have really time to go into the scaling parts of things because we want to do some questions instead. So just to make it short, there's nothing more I can say. I haven't been kidding when I said that there are people storing tens and some even hundreds of terabytes of data in one cluster. Obviously, you need some hardware to do it, but Elasticsearch is really good about scaling horizontally and not vertically. So just to demonstrate, this is the current state on my machine. I'm running 3 clusters. So for the one index, 3 nodes, I'm sorry. So for the one index, that's fairly small. This is the distribution across the nodes. I've decided beforehand that I want to split this index into 5 shards. For each shard, there should be at least 1 replica, so there should be at least 2 copies across the clusters. So you can see 1 row is each node. So if I were to lose 1 node, I still wouldn't lose any data. If I were to add 1 more node, Elasticsearch would just rebalance the shards so that each node would have roughly the same amount of shards. So if anybody is interested in more of these features, let's get together after the talk and not bother everybody else. Right now, there's time for questions. So
That's amazing. Any questions? Yes.
Can you go to one of the first slides with the filters in title?
probably. Okay, that was an easy question to answer. Somebody else? No.
Good. And now the one slide back. Yeah, so are you trying to convince me that the next slide, the query on the next slide, is easier than the previous slide? Honestly, for me, if I would be a user of this API, I would like to ask the query exactly like this.
Yes.
And even more, I can feed this query into post because it easily fits. And this very nested JSON, I can't really do it. So
I understand it's not an easy thing to write. It took me a couple tries to do this. What's important to realize though is you are usually not querying this manually. You have usually some piece of code that will generate those queries for you. And it's usually better to be generating something that's a well-defined data structure than to be generating a blob of text. So we've all been there with SQL. Like, of course, it's very easy to concatenate some strings and get a SQL query, but in the end, you will end up using some sort of ORM, which, if you look at it, it's more difficult. But this is exactly the reason, because this you're working with well-defined data structure. And also, one more thing, because Elasticsearch can actually understand this way better, just the distinction between filters and queries, it will be able to be more efficient about the execution, and you will have so much more power. For example, the multi-match is not possible in this simple syntax.
So I guess this API is not. This API is not intended to be exposed to end users that would like to perform a search, but for developers that would like to develop some search functionality. Yes.
You should never let your users talk directly to Elasticsearch, and even letting them use this syntax is pretty dangerous.
Yeah, but sometimes I would like to expose an API that
yes,
users can use to search something with many criteria.
So you can see here that I'm actually using the DSL. I'm using the query string query, which I can use anywhere when I'm using any other type of query. So I could have a multi-match and a string query. So I'm not losing that. It's not going away. We're just recommending people not to use it because A, it's very dangerous if you expose it to users, because they can then search over any fields, even those that they should know that they're there, and they can do a lot of expensive operations that can actually hamper your performance.
What's the method to incrementally build indices so that to minimize synchronization between search data and actual database?
Okay, so we get this question a lot. We recommend that you just build some sort of queue. If you're using Python, Celery is a great way. So whenever you have a change in database, for example, you're using Django, so you will just use the signals where model has changed. You will dispatch a task into the queue that will then take the model and push it into Elasticsearch. That's how people generally do it. Some people only care about daily snapshots of the data, so they would do bulk loading overnight. There are many ways. I generally recommend using the queue approach with Celery or whatever. Celery is the easiest. I judge by your T-shirt that Django is probably what your poison. So.
You said that there's one data structure which is well defined. So is it formally defined? What do you mean?
Sort of. So I haven't seen a grammar yet. So, but it actually is. So you have on the top level, you always have query and other potential things. A query can either be a core query like this, or some other query, for example, filtered, which again is well defined, that it takes a query and a filter. So it's this composable model that's not defined in one place, but if you actually look up the documentation for filtered query, you'll find this information. It is a query, so you can use it anywhere where you would use a query, but it's also then composed of a query and a filter. And again, a filter can either be this core filter or some other compound filter. For example, a bool filter that range has to be the last 2 years. Also, the rating must be at least 32, 242, and stuff like that. So, yes and no. Any other questions?
You've mentioned something about synonyms. Do you have to provide like a dictionary?
No, it will guess. Yeah.
Or do you specify them in the query, or?
No. This happened at index time. So actually, when you're defining the type, you also define which method should be used for analyzing the text. And there are many options. When we do training, we talk for 3 hours around just that, and it will basically help you define how to break the text into individual tokens, what then to do with the token afterwards. And one of the possible steps is apply synonyms. And you can either give it a file with the synonyms or just list them in the JSON when you're defining the type. So, okay. I'm afraid that we ran out of time for questions. I'll be outside if you wanna ask more. I'll be happy to talk more.
Thank you very much, Hansa.